logical discussion. Science last week. So today what we're going to do is going to study compound propositions, propositions, and then construct tables from them. So just a reminder what we did previously, there were 5 connectives that we used. These connectives act as same things as addition, subtraction, multiplication, division in usual arithmetic. So when it comes to logic, these connectives actually play the same role as we have done for addition, subtraction, things like that. 5 connectives are and, or, not, if, then, if, and, only if, or the two. And writing symbolic form, either Thomas Edison or Alexander Bell invented the telephone, but they didn't both invent the telephone. Okay. I'm sure all of you know Alexander Bell invented the telephone, right? What year was it? When was the Facebook? Okay, coming back to our logic. Step 1, we're going to convert. We're going to write them in symbolic form. This is a compound proposition. It's a mix of more than one atomic propositions. So we split first atomic propositions. One atomic proposition could be Thomas Edison invented the telephone. Let that be P. Okay. Alexander Bell invented the telephone. Let that be Q. That's how you would start. So first we define the atomic proposition at P, the Thomas Edison invented the telephone, and Q, the Alexander Bell invented the telephone. So how you would write this in symbolic form? You done it? P or Q. So either Thomas Edison invented the telephone or Alexander Bell invented the telephone. Now the second half of the proposition is not being done yet. Do you understand? First half of the proposition is either Thomas Edison or Alexander Bell invented the telephone. Now we have to put the second half of the proposition with this. Now there is a condition, but that is acting as AND statement, right? But they didn't both invent the telephone. How you would write that down? Not P and Q. What would be the connective between these two? Here is the one half of the statement. Okay? Now you're going to connect it with another half of the statement. Is it be connected by this arrow, which is if then? Now you're reading it as, if you put an arrow there, you're reading it as if Thomas Edison or Alexander Bell, if either of them has invented the telephone, then you're looking at the other aspect then. So would there be if then, or there would be and statement between them? Okay, so what we have so far, we are there. Someone sent me a message, I don't know who. Muted. Ah, yes. It is, sorry. Okay. So what's the second half then? How would you write second half? First half is this. Either Thomas Edison or Alexander Bell invented the telephone. But now they did not both invent the telephone. First of all, look at both invent the telephone. What that would be? That would be P and Q. This means Alexander Bell and Thomas Edison both invented the telephone. Not. They did not both invent the telephone. Now, what statement we're going to have here? We have to put a connected there. And this connected acted as but. Because this but is connecting this proposition with that proposition. So connecting both of these propositions, we have to use these words to find out what connected would be suitable. So this would be a symbolic form of that, as you can see. Okay. Does it make sense? Right. A common mistake that you guys do in exams, when you're doing it, you don't put connectives between propositions. Almost half of you. It's a very common mistake. Don't forget to put connectives between the propositions. For example, many of you would not write this. It does not make sense if there is no connective between propositions. There has to be something between P and Q. Always. Whatever happens, there has to be a connective between them. Otherwise, let's suppose if you ignore this bar, this proposition would not make any sense. That means if you ignore this and sign, it does not make any sense. Anyway, so in this answer, brackets are used to group sub-expressions within the whole expression. Right. Say, for instance, this is a sub-expression. Either Thomas Edison or Alexander Bell invented the telephone. This expression, they did not, they both invented the telephone. P and Q means they both invented the telephone. And this means not. They did not both invented the telephone. And when we put this together, right, this and between these two propositions, then this is a combined proposition. All right? But they did not both invent the telephone. So there are some principal connectives that we have to keep in mind. Those are between brackets, and then there are minor connectives. We won't worry about minor connectives, but just the principal connectives is the main thing. Okay. So with this expression, we could find its truth value if we know the truth values of P and Q. If we know what P and Q's are, then we can construct truth value for the entire expression. And how are we going to do that? we will find, we'll make a truth table. Well, in this expression, P is a variable, as you would have variable in this expression, 2x squared plus xy plus, let's say, y squared equals to 0. In this expression, there are two variables, x and y. Okay, the arithmetic expressions that you have done, the algebra you have done previously. There is an operation, addition here, which is very similar to what you would have in logic as OR sign. Okay, multiplication is equivalent, this multiplication is equivalent to AND sign. So this is very similar to what we have there in this kind of logical expressions. So remember, I would call this P and Q as variables. This symbol as connectives or operations. Now, what are principal connectives? Principal connectives are a connective that connects to expressions, to major expressions. For instance, there is one expression here and another expression there, and both of them, both of these propositions are connected by this connective. Okay? This connective is called principal connective here. It's just a term. And similarly, in this expression, the principal connective is this OR sign. In this expression, the principal connective is that AND sign. It's just a connective that connects to expressions is called is the principal connective here. No, we don't have to know more about that. Okay, it's just, you just identify, okay, what is a connective? A connective is something that connects to expressions. And it's called principal if it connects to major expressions there. So, in this, as I said, this is your expression A, this is your expression B, it is connected by this symbol, so this symbol is principal connective. Okay, let's make some truth tables. A logical expression such as this can be analyzed using a truth table. So let's try to construct a truth table here. I would like to do that right from scratch. Reason being, because this is what we're going to do in the next 3 lectures as well. So first of all, you have to find truth values for P or Q. Okay. So to start with, you write P and Q and list all the possible values. So what are the possible values for P? Either it could be true, false, false. These are the possible values of P. Okay. Always. Q, think of them as a coin. Okay, there you've got 2 coins, P and Q. You flip them. It is possible that both are head. It is possible one is head, other is tail. It is possible that one is tail, other is head, and it is possible both of them are tails. You agree? So you're flipping 2 coins. What are all the possible outcomes? Possible outcomes are both are head, both are tail, one is head, other is tail, the other is head, and the first one again is tail. So these are all the possibilities of flipping 2 coins. Now, in this expression, I have to logically or systematically proceed. So I'm going to form a truth table. So first of all, I have P, Q. Now next thing I'm going to do is to construct table for what is this bracket, P or Q. So when you flip 2 coins, if your statement is true or other statement is true, that means P or Q is true, right? True or true is true. True or false is true. If one of them is true, we are done. If both of them are false, then it is false. You agree with that, right? This is your this bracket done. So next thing we have to worry about is this bracket. P and Q. P and Q. If one statement is true, other statement is true, then it is true. If one statement is true, other is false, then AND statement will give you false answer. False, false. You agree with that? Okay. Now, what's the next thing I'm going to do? I'm going to construct table for, I have to put not there in this bracket. So that means not P and Q. So you have table for P and Q, and then you're going to negate it. That means opposite to what you have. So that would be false, true, true, true. Do you agree with that? Okay. And finally we have this statement as A, this statement, let's call that as B, and I have to now find out A and B. So remember, this is A, that is B, and the connective in between is and. Okay, now we have two columns, A, and we have another column, B. Now we have to find the truth values for A and B. So this is true, that is false. So this is going to be, if you put and between true or and false, it has to be false. That has to be false. That has to be false. And the last one has to be false. No, I'm not. You know where I am from. Yep, this is that. But that presents an opportunity to know that it's possible that the end column that you're getting, it may well be all true or all false. We have a specific name for that. I'll come to that in the next example. Anyway, so this is true and that is false. So AND statement will give me false. And the next two are then truth, and false and true is false. So I have this as my answer for this expression. False, true, true, false. While looking at all of these columns, do you see anywhere this column is equal to? So we don't get an equivalent statement for that. Okay? So if any of the column is equal to that, then that column would be a simplified version of this expression. Any questions? All right. Fantastic. There are no questions. You should be on top of constructing these kind of tables. I have done step by step whatever presented here. All right. So at each step, the truth values are found using truth tables, and that's how we construct them. And you can see what we had. We had okay, these are the truth tables. We don't have to worry about that. We actually constructed this table from scratch ourselves. So whatever discussions I have put over there, we discussed that already. All right. If you understand that, you don't have to go into this truth table at all. Now, using the truth table, so in the symbolic form, this expression represented the statement: either Thomas Edison or Alexander Bell invented the telephone, but they didn't both invent the telephone, right? Now, while looking at the previous table, you all know that who invented the telephone?
Tesla.
Telephone.
Bell.
Alexander Bell. Tesla invented the, what Tesla did? What?
Tesla coil.
Tesla coil. Yes, you were absolutely right there. Why? Mm-hmm. Yes.
Didn't you seek to make a wireless energy grid using electrical currents through the atmosphere?
Absolutely right. Tesla believed that these energies and all that should be free for humans. And you could get them from sun, all these energy and everything from environment. And of course at that time, when it was nearly, I think 70, 80 years ago, you know, the corporate businessmen at that stage, nobody was in favor, of course, to have energy for free for people. Who would like that idea? So that's why it did not receive much attention at that stage, but recently a lot. Okay.
Wouldn't the system that we use run on computers that we use today?
I don't know much. I can't. You have to read more about that. But it was like sort of this Tesla coil. Yeah, there are lots of other inventions he did. Yeah. Anyway, so Alexander Bell invented the telephone, and we referred that statement as P, I think. What was that? P stood for. Let me see. Okay, P was Edison and Q was Bell. Okay. So while looking at it, P was Edison, so it is clearly false. Q is true. Alexander Bell invented the telephone. And when we go all the way, this line, your end expression is a true expression. So the statement, the proposition that given to you is a true proposition. That's how we're going to read this. Okay, so from the truth table, so given Thomas Edison invented the telephone is false and Alexander Bell invented the telephone is true, the truth table on the previous slide tells us immediately that the proposition is true. There are some propositions, however, which are self-referential sometimes, and they are ultimately, whatever their input value is, they are always true. Okay? And there are some statements, whatever your input value, they're always false. We're going to look at them soon, but first notice that in the previous proposition we had only two variables, P and Q. And how many rows did that form? Do you know how many rows were there in the previous table? 4, absolutely right. Now think if there is a third variable. Think of that as flipping a coin. Now think of that having 3 coins. How many times you would expect that, how many possible different outcomes you can have while flipping 3 coins together? Anyone else? So suppose you have 3 coins. The possibilities are you flip all of them together, you got head, head, head. Then head, head, tail. Head, tail, head, tail, head, head. Yeah? Agree? Head, tail, 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 head, tail. And then tail, tail, head, tail, tail, tail. Is that right? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possibilities. So if you have a proposition where there are 3 variables, suppose P, Q, R, possible that you would have true, 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 false, true, false, false. Keep going like that. Okay? So, what you think, how many possibilities you're going to get? 8. Exactly. These rows, number of rows you would have, so this would be false, false, false. There will be 8 rows together, all of them. 2 to the power 3. If there are 3 variables, 2 to the power 3 number of rows, possibilities. If there are 2 variables, 2 to the power 2, 4 possibilities. If there is 1 variable, there are only 2 possibilities, true or false. So this is the variable, that's the variable, that's the variable. Okay. Now, yeah, I will explain that. If a logical expression has 5 variables, how many rows are there in its truth table? Come on.
64?
Nope. 32. You were just 2 ahead. 2, 4, 8, 16, 32. Yeah. So for each new variable that is included in the truth table, the size of the table is double. So the table grows exponentially. Remember, when there are 7 variables, the rows would be 128. Jump from 64 to 128 is huge, actually. By adding 1 variable, grows double. And of course, if it is going bigger and bigger, if there are more and more variables, then the table grows exponentially. Anyway, let's look at a few more examples. I really want you guys to understand that. If Mary and Michael are not both left-handed, then either, now here comes that arrow sign, then either Mary is not left-handed or Michael is not left-handed. Can you write this in symbolic form first? So step 1, we're going to name atomic propositions in it. No writing? Oh, sorry. Turn it on. When you write it in exam, you have to write it properly. You would say, let P denotes Mary is left-handed. Mary is left-handed, let that be P. Michael is left-handed, let that be Q. Okay? You will not put not and other and connectives in the proposition when you are naming them. Fantastic. This is the way we're going to do that. Yep. So this reads as Mary and Michael are left-handed. Not. Okay? Mary and Michael are not left-handed is this. If then. So if Mary and Michael are not left-handed, then. So this is how this proposition reads. Then Mary is not left-handed, not P. Okay. Now we want to analyze this, whether this is a correct statement or not. What you guys think? Is this correct? So remember, what you're looking at, Mary is not left-handed. Second half of the proposition, if you look at after, then either, look at afterwards, then either, there are two propositions further. Mary is not left-handed, connected by another proposition, or Michael is not left-handed. So you have to see further, after either, there is a compound proposition that is connecting two propositions. Mary is not left-handed, or Michael is not left-handed. That it is connected by that symbol or. Fantastic. Okay, so the next part, then either will complete. We have completed this part. Now look at the rest of the part and treat it as sort of an independent proposition. In there are two halves, this and that, connected by the symbol or. So what we have there then, Mary is not left-handed, not P. Or Michael is not left-handed. Now here we don't have the word both that you put and with. Here is the word Mary is not left-handed. That's one independent statement. Or connected with another independent statement, Michael is not left-handed. Okay? So this is your statement. Yeah. A logical expression. Now, from its truth value, if you look at, just observe, in this proposition is always true. Do you agree with me? So we first said, we are giving a fact. The fact is, if Mary and Michael are not both left-handed, that's an if statement. So we've given a fact that both of them are not left-handed. So that means at least one possibility is true, that at least one of them is not left-handed. Okay. So this has to be true. We can check it by constructing the truth table. The truth table gives us, I'm not going in that detail, so you can see P and Q. First you draw this value, and then you make this not there. So you have the left-hand part. So this left-hand part, first you drew that. Then you constructed this table for that value on the right. And then you connected them by implications. So you see, if the tail is false, whatever head is, it has to be true. Remember, last week's discussion, I said, if my claim is, if Sue attends discrete math tutorials, then she passed the subject. But if she does not attend, It doesn't matter to me, whatever my claim is still true. My claim is only false if she does not attend the tutorials but she passed the subject. I am granting if somebody attends tutorials, through my statement, if somebody attends the tutorial, then she passed the subject. But if someone does not attend tutorial but pass, that means my claim is wrong. All right? Oh, no, sorry. Yeah. If somebody attends but fails, then my claim is wrong. But if somebody does not attend, it does not matter. My claim is valid. So look at here. If tail is false, my claim is true, irrespective what outcome is, head is. So if the tail is true, and that is true, it has to be true. So you can see these are true statements, so all of them are true. As I said at start, that from this expression I can see that this expression has to be true every time. Every time. Because this is a logical conclusion. Do you agree? Any questions? So this is how we construct a table, and if in the final column you get true, 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 all of them are true entries, it is called tautology. Universal truth, in other words. It's a tautology. And if all the statements are false, that's a contradiction. So the truth table on the previous slide shows that the logical expression is always true irrespective of the truth values of P and Q. Such an expression is called tautology. Okay? And if all the expressions are false, then that statement would be contradiction. Now look at this. Consider the proposition, Anne is happy, Anne is neither happy nor wealthy. Now, while looking at the statement, is sort of, if we draw a truth table, what's she going to get? False. Yes, it's a false statement. Anne is happy, and then we're putting something else. Anne is neither happy nor wealthy. There is a contradiction in that statement. But we have to use these logical expressions to draw conclusions. And how are we going to do that? We allocate variables. Anne is happy is our atomic proposition P. Anne is wealthy is atomic proposition Q. And then we're going to draw a table for that. So Anne is happy, let that be P. Anne is wealthy, that be Q. And our statement is Anne is happy P, and Anne is neither happy nor wealthy. So we're going to construct truth table for that, and when we do that, what we're going to get? We're going to get all false in the last column, and such a statement is called a contradiction. So remember, if you want to prove something, right, that something holds, you have to get tautology. And if you want to disprove something, you have to say that in all cases you're going to get a contradiction. That's what normally happens when you're proving something. But, yeah. Anyway. And sometimes you get an expression where the last column gives you true, false, true, true. That means this is neither tautology nor contradiction. So we just named a few things. If you get all T's, then it's a tautology. If you get all F's, it's a contradiction. All other cases are in between. Neither tautology nor contradictions. Questions? So by now you should be able to construct, firstly look at atomic propositions, use the connectives, construct truth tables, and find the truth values. You should be able to do that. And you should be able to analyze propositions as well. Now, I'm just going through a few more examples. Let A today is Friday and the sun is shining. Okay? And B, the sun is shining and either today is Friday or the sun is not shining. Just, yeah? So A is also a compound proposition because it is connecting today is Friday, it's P, sun is shining, it's Q, and it is connected as P and Q. Yeah? That's one compound proposition. And the next one, the sun is shining, which is Q, and either today is Friday, it is P, or sun is not shining. This B is also a compound proposition. Okay? Now, as you can see, we want to find out which one is true, which one is false, or what are their truth values. We're going to construct truth table for that. So we define atomic propositions as I just stated. Now develop truth values for A and B combined into one table. So let's look at that. So today is Friday. This is your A proposition. Okay? And your B proposition is here. So the truth table for A is this, and truth table for B is that. No, both of them are not tautologies or contradictions. So basically, to draw conclusions, we have to know if it is Friday or not, if the sun is shining or not. So we have to know their truth values. If it is Friday and sun is shining, then this is true. Yeah? In all other cases, it's false. Similarly for the other. So now we want to draw another conclusion from here, that this 2 is actually equals to 1. Both of them are giving us exactly the same conclusion. Do you agree with me? Yeah. So instead of writing this complicated expression, we can replace it as P and Q. By these 3 lines, we mean equivalent to. For example, 1/2 is not exactly equals to basically 2/4. We normally say it is equals to, but these are congruence classes. That when we say that, okay, you can remove equivalent classes. This means 2 out of 4. This means 1 out of 2. Like 4 apples, you choose 2 from them. 2 apples, you choose 1 from them. These are equivalent statements, not exactly the same. Yeah? But in arithmetic, we put an equal sign. That, okay, in arithmetic, this is equal. But when it comes to logic, logical expressions, there are lots of possibilities. This is very similar to 3/6. Choose 3 from 6. Right? We cannot say this is exactly 1/2 in that sense, when it comes to logical expressions. So therefore, we use this symbol of 3 lines to say that this is equivalent. Right? So 1 and 2 are identical, and we put them. We are saying that these are logically equivalent. So the general definition is 2 expressions are logically equivalent if they have the same truth values for every combination of the truth values of those variables. Okay? You don't have to really write it down, it's just an observation. Okay? What we did so far today, we simply learned how to construct truth tables. There were some general notions, like for example, principal connectives. Of course, connectives, like if you have compound proposition, another compound proposition, something that connects with them is a principal connective. Yeah, sure. You know that. Okay? If one entire column is equal to another entire column, so we will say that these are logical equivalent statements. And then we said, all right, if in one column you get all truths, then it's a tautology. If you get all false, it's just a contradiction. And before we conclude, let's look at the last example. Consider the proposition, Anne is neither happy nor wealthy. Okay. The atomic propositions can be defined as N is happy, that's P, N is wealthy, that's Q. Okay? And then neither happy nor wealthy, that means first we're saying either happy or wealthy, not. So neither happy nor wealthy. Okay? This can also be written as N is both not happy, not wealthy. You can also write like this. So in other words, what we are saying, not P or Q is equivalent to not P and not Q. When you use this operator not inside, then it switches this or sign into and. Let me give you more example. A intersection B. Did you do sets previously in math for IT? Did you do some kind of union, intersection, and complement? It doesn't matter if you have not. It does not matter. We are coming from a simple observation here. The simple observation that we have noted is that if you put not outside, P or Q, not outside, this is the same as to say not P, not Q, but you're going to switch this or with and. This is exactly the same if you have A and B complement. This would be equals to A complement union B complement. In the next topic that we're going to do, we're going to study these kind of things. Okay. We'll do it then. For the time being, we have just noticed this this truth of this equivalence. So in other words, not P or Q is equivalent to not P and not Q. We need this when we're going to use them frequently, these kind of equivalences, when we're going to solve logical expressions. What you notice so far, constructing table takes time, right? We want to replace that. We want to find equivalent values without going through truth tables. We don't want to do that. So, and in order to do that, we have to rely on these kind of equivalences. We would simply use these expressions. We simply solve expressions without going to find their actual value. For example, x squared minus 4 equals to 0. Yeah? You don't have to really find what is x here to satisfy this equation, right? But if you solve this equation, you will eventually find what x that would be. So from there, you can imply x is equal to plus minus 2. That's an implication from here, without being stuck there, see that, oh, what x would satisfy this. Or suppose this is something a bit more complicated, x squared plus 2, xy plus y squared equals to 0. For what values of x and y this is satisfied? For all those x and y which are equal to each other, right? With a negative slope. But you can simplify this by writing it down as x plus y squared, things like that. So you didn't know what an x and y exactly are. Is it x is 1, y is negative 2, y is 5, x is 3, something like that. You don't allocate values. Okay? You treat them as sort of some general variable and you find their values in the end solutions. Similarly, the truth tables we are constructing, these are just intermediate steps. We can bypass them. And how are we going to bypass them? When we treat these kind of expressions as equations, and then we simplify them. Okay, that's what we will do in forthcoming lectures. And yeah, that's where we stop. Any questions? Please let me know.